since I wasn't there today, and you can watch this video and pause it wherever you'd like, take some notes, so that we can keep on moving with our class today. You want to say hi, Zach? Say hi. Alright. So, in an RL circuit...
Oh, how life has changed in 1 year. That was a video of my first flip. I'll leave a link in the description if you want to watch the same lesson that I'm about to do right now, but for the very first time. So what we saw today in the lab was that if we have a moving current in an inductor creates a magnetic field. Remember, it's just a solenoid, and like capacitors where we had two plates and separated charges and stored the energy in electric fields, now we can store the energy in the magnetic field of an inductor. So if we want to turn the amount of magnetic energy stored in the magnetic field, what we need to do is do a Kirchhoff loop around this setup. So your loop initially looks like this. You've got the voltage in the battery minus IR minus LdI dt, the energy that's put into the inductor and the magnetic field. If I want all these values to be positive, I just have to rearrange, and you get this. But this just tells me the energy per charge. It doesn't tell me anything about the amount of power or energy given to each of these devices per second. To do power, remember, for a battery, I've got to do I times V. And if I do I times V, that's going to indicate the amount of watts the battery is going to provide, the amount of joules per second. Well, if I multiply that by I, I've got to multiply everybody by I. So I get I squared R in the resistor. Remember, that's the power of the joule heating in the resistor per second. And that means I have to also multiply LdI dt by another I. What this highlighted area is going to show us is the amount of energy given to the inductor every single second. And the energy is going to go in the form of a magnetic field. So writing what the definition of power is, remember, power is the energy per second. That's also going to equal Li di dt. There's a dt on both sides, so I can eliminate that and leave myself du equals Li di.
As big as a whale, hidey, 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 high. Hody, 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 ho.
That means I have to integrate both sides, from which du, we're going to go from no energy to all the energy, so du is just going to become u, and the bounds for Li di is going to be from no current to maximum current. Doing the integration, magnetic potential energy is going to be equal to 1/2 Li squared. Remembering that energy is in joules, that means a Henry times an amp squared should also give you joules. So make sure you go back and double check that you can get that unit. Now, one thing we talked about in terms of capacitors was the energy packed in the volume between those two plates. Well, since there's a volume for a solenoid, we can also figure out the amount of magnetic energy stored in that volume in the magnetic field. So the magnetic energy is 1/2 Li squared. Remembering that the inductance is unique for each solenoid, and the current comes from the magnetic field set up in that solenoid. So we can substitute out L and I, where L is the inductance based on the geometry of the shape. So mu0 little n squared AL. I know in the last video it was mu0 big N squared area divided by length, but if you want to substitute little n in, you can get this formula for your inductance. The current in a solenoid comes from Bunny. If I want to solve for current, I get magnetic field over mu0 little n, and I've got to square that whole thing. What we're going to get is some cancellation here, like the little n's will cancel, one of the mu's will cancel, and we'll be left with a b squared. So you get b squared over 2 mu0 multiplied by area times length. Well, area times length, remember, is the volume. And the question was, how much energy per unit volume do we have inside the solenoid? So if I divide by the volume, I get magnetic energy density in the form of b squared over 2 mu0. Now, we did this before with electric fields, like I said, and in electric fields we found out the energy in the electric field per unit volume came out to 1/2 epsilon 0 E squared. So it's similar to the magnetic field energy density, except it used permeability instead of permittivity, like they did with electric fields. So now we're going to look at RL circuits instead of an RC circuit. RC was a resistor and a capacitor, and an RL is a resistor and an inductor. Since the inductors are going to create back EMFs, remember, as soon as we close the switch, the battery is going to try and push charge through the circuit, but the inductor has no flux in the beginning, so it's going to create a back EMF to try and resist the battery from setting up a magnetic field inside of it. So some of the places we're going to be concerned with are at the beginning, as the current grows, and when current is max. So here we are with our circuit, and we made a Kirchhoff loop. Down at the bottom, it's voltage minus IR minus L di dt. And at the start, we can say that there is no flux, because there is no magnetic field that is in the solenoid. As the current tries to set up a magnetic field and magnetic flux in the solenoid, it's going to resist it with a back EMF and basically be an infinite resistor, which means that at the very, very start, the current is going to equal 0, which means I can take out this part of the equation and simplify our loop to this, that the voltage in the battery is going to equal the voltage across the inductor, and they're going to fight each other to try and resist the change in flux in the inductor. If I want to know how many amps per second I'm going to be able to pull, I can divide by the inductance on both sides and get voltage over inductance to be the rate of change in current in my circuit. Now let's look when we get to the very end of the circuit, when current has ultimately won. So when we get to the maximum current, now you can see current is flowing through the circuit. There's a magnetic field that's set up in the inductor. The inductor is now used to the magnetic flux, and so it doesn't really care anymore. What that means is that the current is not changing. The current is now constant, which is going to wipe out this equation in my Kirchhoff loop. And if I do that, I can basically say that V equals IR, which is what we've said all along with Ohm's law and what the inductor truly is. The inductor is just a coil of wire. There's current running through the wire, so there is nothing to it, and there's basically no resistance in the inductor anymore. So it's like the inductor is not even there when this acts purely as a wire. So really, if I wanted to solve for currents or resistances or voltages, I could do everything I used to do back in chapter 25 with the direct current circuit. V equals IR. And at this point, the resistor is heating, so it's giving off energy per second, whether it's giving off heat, light, sound, whatever that resistor is trying to do for your setup. So now we need to go back when the current is growing in your circuit. So as the current grows here, you can see that I'm not at maximum current yet. The magnetic field is slowly increasing, and the resistor is lighting. And if it's a light bulb, it is heating, but it's not at maximum output yet. So that means that all three of those factors at the bottom are in play. The voltage, the IR in the resistor, and the L di dt in the inductor. If I wanted to solve for the change in current with respect to time now, I can rearrange this formula and get this. di dt equals V minus IR over L. And that will give me the amount of amps per second growing in the circuit at this particular moment in time. The trouble is, I need to know the current at that particular moment in time, and this is where integration is going to come in. So looking back at our Kirchhoff loop here, V minus IR equals L di dt. I want to get all the dt's and di's on the same side. So rearranging a little bit, I get dt over L equals di over V minus IR. Now, I have an I and di on the same side, but there's a couple extra things, there's a little bit of baggage with it. So let's integrate the left side first from 0 to any time t. And that's going to be an easy integration. It's going to give me t over L. So the other side, I'm going to suggest we do a u substitution to try and get di and du into a common term. So we're going to let u equal V minus IR, and du, since voltage is a constant, we can get rid of that and leave us a negative di times R. But in the formula we had di, so I have to get di by itself, so I can substitute that out, and it gives me du over negative R. So let's go put back in what we have for V minus IR and what we have for di. So I get a negative 1 over R is the integral of du over u. So I can move over the negative R to do negative R over L times time equals the integral of du over u. Integrating that gives us the natural log of u. And we're going to do that between our two bounds, between no current in the beginning and our maximum current at the end. So substituting back in for u what u actually is, so I get the natural log of E minus IR over the voltage, and I want to get rid of my natural log like we normally do, so we're going to raise that to the E power, and what that's going to get me is e to the minus t over tau. I'm going to substitute out the R over L for my time constant like we've used for RC circuits. My time constant now is going to be L over R. So if you take the inductance over a resistance, you should get a second. So go through the unit derivation again and prove to yourself that an L divided by R is a time constant. just like an R times a C. A resistance times a capacitance also gave us a second. So doing some rearranging and solving for current, I get this set up, but I need current by itself. Well, I see current over here, and I can get it if I divide by R, which means I'd have to divide everybody by R. So the R cancels there, leaves me a resistance underneath that voltage there, and a V over R on the other side. So this should simplify a little bit more for us to this. V over R minus V over R e to the minus t over tau. In the form of this, voltage over resistance times 1 minus e to the minus t over tau. But remember, V over R is current. Well, which current is that? Well, that ends up being our maximum current. So if you know what your maximum current is going to be in the end, you can figure out your current at any moment in time with this setup. So as the current grows, the inductor starts to energize, and as it energizes, we can play the game where if we get to one time constant, we're over 50%, we're around that 3% of our maximum current. If we're at 2 time constants, we're up around 80% of our maximum current, and when you get to 4 and 5 time constants, you're at the maximum current. The inductor has now become a wire. Once we get to our maximum current, it's like the inductor has now become a wire, and it's like the inductor is not even there. So if you look at my setup here, I see a battery with 2 resistors in series. And I don't have to worry about the inductor because we're past that time when the current is growing. So I can just do 2 resistors in series with a battery and figure out currents, energies, what have you. But what if I want to cut out the battery? Well, when I cut out the battery, I use the special switch called a make before break switch. As I move the switch from E to F, it's going to make contact with that secondary loop before it cuts out the battery. Once it cuts out the battery, then this will be my entire loop. It's going to be one resistor with the inductor. And the inductor is going to be cut off from the current, so the magnetic flux is going to decrease, and the inductor is not going to like that. It's going to want to try and power the circuit and keep things going. So what would an equation for that look like? So when we de-energize the coil, our loop is just minus IR minus LdI dt. We cut out the battery because there's no more energy provided from the battery. So the inductor is going to pretend to be the battery for a while. So rearranging, getting the I's and DI's together, you're set up with this. DI over I equals negative R over L dt. You can see we already have our time constant in play. So we can see that on the current side, we're going to go from our maximum current now to any current at any moment in time, and for the time we'll go from time 0 to any time t. Integrating both sides, you're going to get the natural log of current over the maximum current equals negative R over LT. We want to get rid of the natural log again, so you get this, e to the minus t over tau. Solving for current, you get that the current at any moment in time is the maximum current times e to the minus t over tau, which looks just like when a capacitor was discharging. It actually follows the same setup, just at a different curve based on the inductance and the resistance. So when the battery is removed, the inductor is going to try and maintain the current, use that magnetic potential energy to continue the flow of charge. So on AP tests, they like to ask you when the switch is thrown, after lot's time, and maybe the amps per second while the current is growing at a particular moment. Not necessarily the whole derivation we just did, but knowing what's happening as you're either growing or discharging in the inductors. So I'll let my first flip video sign off.
The circuit, RL circuit, as the inductor starts to energize, I always slip up and say that it's charging because I'm used to saying grow exponentially at this 1 minus e to the negative t over tau, which means that, alright, Zach's going to take a break, that L over R has to give us a second, and we'll talk about that tomorrow.